Hello, welcome to Pakibi TV. In this video, I will explain the topics of set theory and infinity. This is a video that explains why set theory is necessary in mathematics. Why and how does set theory deal with infinity? That's the topic of this video. In the previous video about set theory, I did not explain one of the important reasons for its importance in mathematics: infinity. That is, the main explanation was that set theory provides a powerful methodology for integrating the system of mathematics. Now let's focus on infinity, another topic where the powerful mathematical power of set theory is revealed. This topic consists of two questions. The first one is, why did we come to deal with infinity in mathematics? And the second one is, how did Cantor, the founder of set theory, handle infinity? For this question, I will introduce an example we can agree with while introducing what Cantor tried to solve. In this question, I won't just explain the contents of a set theory textbook dealing with infinity, but will also explain its mathematical thinking. The explanation will be a bit detailed. Why do we need to deal with infinity in mathematics? Because many things in mathematics are infinite. For example, like this. Here, if you keep adding 1, 4 to 1, 2 infinitely, the total becomes 1. Here we have a calculation where an infinite number of numbers are added. Even before that, the number of natural numbers, integers, and real numbers themselves are infinite. It's just there from the start in mathematics. We have to deal with these mathematical entities that have infinite characteristics in mathematics. And by that, I mean mathematically. When we say mathematically, it means logically, and it implies dealing with it in the way of counting numbers. Until a man named Cantor appeared and created set theory, mathematicians avoided this problem. What kinds of problems were so difficult for mathematicians to avoid? There are infinitely many natural numbers, integers, and real numbers, but which is more numerous, the number of natural numbers or the number of integers? It seems like there are more integers, right? But, after all, both are infinite. They are the same in being infinite. The counts are the same. One is more, but at the same time, it is also the same. Something doesn't match up, right? Since logic is important in mathematics, such inconsistent thoughts are fatally problematic. Cantor provided a very good answer to this. So, how did Cantor handle infinity in set theory? The specific problem is measuring infinite size. It's about checking whether integers are more numerous than natural numbers. The question is how? How do we measure infinite size? Cantor's answer is one-to-one correspondence. So, when measuring the size of natural and integer sets, we look for a way to make a one-to-one correspondence between natural numbers and integers. In conclusion, for natural numbers and integers, if they are lined up like this, everything becomes a one-to-one correspondence. So the conclusion is that the number of natural numbers and integers is the same. Now, do you understand? But if you think, well, it seems plausible, and you don't accept it right away, you only know the shell of the thought, and you haven't understood the core. Mathematics is a study of necessity. If you understand it fully, everything will seem so obvious. So, I'll explain more. All right, let's start from the method of measuring the size of infinities, the one-to-one correspondence. Why do we need to compare counts by doing a one-to-one correspondence? Can't we do it in another way? Let's say we have these two sets, and there are a lot of elements in them. Let's compare the number of elements in the two sets. This side has more. Yes, exactly. How did you know that? You thought about the fact that one is left over here. The way we just thought is exactly a one-to-one correspondence. In other words, when considering which set has more elements, the way we usually think is one-to-one correspondence. In simple terms, comparison itself is one-to-one correspondence. When Cantor thought one-to-one correspondence when comparing the size of infinite sets, he wasn't discovering some unusual method different from others, but he was applying the original way we compare the number of objects. Cantor's discovery is not merely creative, but it is a philosophical insight. It's what philosophy is, to find our fundamental thoughts that we are not fully aware of. Some of you might think like this.
I just counted the numbers without making a one-to-one correspondence.
That's possible. There are 6 on this side and 5 on that side. Although there are teachers who do not like such seemingly impertinent questions, these questions are absolutely necessary. To answer this first, without doing a one-to-one correspondence and merely counting the number. In fact, Cantor thought that this was equivalent to creating a one-to-one correspondence with natural numbers. This is a universally accepted claim. For instance, claiming that this set has 6 elements implies that we've applied this kind of correspondence. Ultimately, thinking that one side has 6 and the other has 5 is nothing more than doing a one-to-one correspondence twice. Here, we've already answered the second question as well. Can't we compare quantities in a different way? There aren't many other ways. Perhaps a very creative person could conceive a different way to compare numbers. But as of now, our conventional method of comparison has been one-to-one correspondence. Now let's examine the details of comparing infinite sets using the one-to-one correspondence method. Consider this. You'll likely understand that the count of natural numbers and integers are the same through a one-to-one correspondence. However, there are various things to ponder upon. If we don't address these and move on, you'll just end up memorizing it instead of understanding math. Firstly, no matter what, the most crucial question is this. Sure, I understand that if there's a one-to-one correspondence, their counts are the same. But even if their counts are the same, isn't it possible that they can't be paired in a one-to-one correspondence? Secondly, when they can't be paired in a one-to-one correspondence, how can we determine if they have the same count but can't be paired, or if they have different counts and that's why they can't be paired? Thirdly, if they genuinely can't be paired due to different counts, is there a way to know that? Starting from the first point indeed. Even if the count is the same, we may not be able to map them one-to-one. Considering there's an extra z here, even if the counts are made equal, wouldn't they mismatch when we try to map them? While it's easy to see this when there are only a few elements, it becomes unpredictable when there's an infinite number of them. However, the key point is this. Although there may be incorrect mappings, if we can map them one-to-one even just once, it means the counts on both sides are identical. Moving on, this might be something we never truly find out. That's why someone makes it their profession. That person is a mathematician. When a mathematician finds and shows a one-to-one mapping method, in that case, we just need to understand. The number of elements in both sets is the same. Following that, firstly, there is a method to show that the number of elements in two sets is different. The way to demonstrate that the count of infinite sets is different is called the diagonal argument. However, it's uncertain if we can always prove that the count of the two sets is different. In this way, Cantor proved, for his time, some astonishing results. The number of natural numbers is the same as the number of integers. The count of natural numbers is also equal to the count of rational numbers. The count of real numbers is greater than that of natural numbers. Also, the number of points on a line segment is the same as the number of points on a plane. These are among the things he proved. I mentioned to you that mathematics is a discipline of necessity. The inevitable and logical things are generally obvious. Like 1 + 2 = 3, it's so intuitive that it's almost boring. Thus, things that go against intuition are generally not mathematical truths. However, such things happened in set theory. Natural numbers are a subset of integers, and integers are a subset of rational numbers, but he proved that their counts are the same. So initially, mathematicians didn't accept Cantor's set theory, but eventually they did. Why? The structure of mathematical thought can be represented as a triangle like this. From here, based on what's very obvious, we progress to a new truth. This progression is based on extremely strict logical reasoning. For an understanding of the systematic nature of mathematics, please refer to this video. In set theory, one of the concepts that fits this is the idea that comparing quantities equates to a one-to-one correspondence. Cantor was the first to articulate this clearly, but in reality, it's a fundamental way of thinking that exists in everyone's mind, so it's undeniable. From this, because such a conclusion was drawn, you can only say it's incorrect if you either discard this and start from another premise, or there's a logical issue in this process. However, apart from a one-to-one correspondence, how else can you compare quantities? There is no other way. Therefore, it's impossible not to accept Cantor's proofs. In set theory, I briefly explained why infinity was addressed and how it was mathematically handled. I skipped explaining the diagonal argument in the middle, fearing the video might get too long, but I'll cover it in the next video. If this video was helpful, Please hit the like and subscribe button and turn on notifications. Thank you.